As I mentioned in my last video, I watch Globers explain the globe and I sometimes doubt whether or not they are right. MC Toon was the first one I addressed, and I'd like to emphasize that he is one of those Globers I admire for their patience and knowledge when debating sometimes unbelievably ill-informed flurfers. The fact that he and others sometimes deliver simplified explanations should be considered as a handicap that comes with debating morons or explaining phenomena to the general population, those that don't deal with physics regularly. That still means that you have to try to be as concise and accurate as possible. When I heard FTFE explain the demonstration of Foucault's pendulum by mentioning the Coriolis force as the cause of the pendulum drifting, I had my doubts.
So with just the data gathered from the swinging pendulum, they were able to calculate their latitude on Earth because of the Coriolis forces applied due to the rotating Earth.
Could Coriolis affect a pendulum swinging so slow and over such a small distance in such a way that the drift would be noticeable? In high school, I had heard from my physics teacher that an object free moving in a circular pattern forms a rigid plane in space, a plane that keeps its orientations at all time because of conservation of angular momentum. Because the pivot point of the pendulum is moving with the rotating Earth, the rigid plane established by the swinging pendulum starts deviating relative to the ground. And the Coriolis explanation seems to me a somewhat far-fetched one. I decided to open my spreadsheet that I developed for my Coriolis video number 34 again and put in the numbers. I took the video that FTFE shows when explaining Coriolis and tried, as best as I could, to derive the necessary data from it. The latitude of the experiment was clear, 48.4 degrees. The speed of the pendulum was a little more complicated. The length of the trajectory at its largest I calculated to be 2.75 meters, and the time it took the bob swinging one period was 5 seconds. But the pendulum was swinging over an increasingly smaller length, and at the end I calculated the swing at 4 seconds at a length of 1.1 meters. So an average of 4.5 seconds over a distance of 1.925 meters. The total time recorded was 0.688 hours or 2,477 seconds. The total distance covered was therefore 1,059 meters and the drift would be 7.67 degrees. And what was the drift measured in the demonstration? Right, 7.89 degrees. The prediction was 2.86% off, quite accurate considering that I had to calculate the length of the trajectory by counting the number of A4 sheets of paper, of which some overlapped, and that I could only time the period in whole seconds. I also had to assume that the decline of the distance covered develops linearly. Also, I assumed that the direction of the swing was due north-south. I think you could say that the results of the Foucault pendulum was absolutely in line with the expected drift caused by the Coriolis effect, and FTFE was absolutely right to mention it as the explanation of the drift of the pendulum. Well, he was not completely right. He mentioned the Coriolis force, a force that is inertial or fictitious. It is fictitious in the sense that the plane in which the pendulum swings does not drift. So there is no sideward drift to the pendulum itself. So there is no sideway acceleration, therefore there is no force acting upon the pendulum. The pendulum only seems to drift relative to the rotating Earth. This drift is perceived as a sideward acceleration, and because of Newton's second law of motion, force equals mass times acceleration. If there is an acceleration, there must be a force. We call it Coriolis force. In reality, that force is fictitious because the acceleration is only apparent. It is not a real force. To avoid an extra complication, when some flat earther wiser guy starts about the Coriolis force not being a force, FTFE better mention from now on Coriolis effect instead of for Coriolis force, and then he would be dead right.